This chapter discusses accessing big data. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Bassens, and I'm one of the authors of the book. In this chapter, we zoom into big data. We kick off by reviewing the 5 V's of big data. Next, we zoom in on the common big data technologies in use today. We discuss Hadoop, SQL on Hadoop, and Apache Spark. Data are everywhere. To give some staggering examples, IBM projects that every day we generate 2.5 quintillion bytes of data. Every minute, more than 300,000 tweets are created. Netflix subscribers are streaming more than 70,000 hours of video at once. Apple users download 30,000 apps, and Instagram users like almost 2 million photos. In relative terms, 90% of the data in the world has been created in the last 2 years. It is important to note that big data encompasses both structured and highly unstructured forms of data. In a 2001 research report, Gartner set out to define the scope of big data by listing its characteristics in the now famous 3 V's. Volume, the amount of data, also referred to as the data at rest. Velocity, the speed at which data comes in and goes out, data in motion. And variety, the range of data types and sources that are used, data in its many forms. Many vendors and industry actors continue to use these V's to describe big data today. In recent years, vendors and researchers have also argued for a 4th V to be included in the description of big data: veracity, or data in doubt. It describes the uncertainty due to data inconsistency and incompleteness, to ambiguities present in the data, as well as latency or certain data points that might be derived from estimates or approximations. Finally, to emphasize that being able to store or process these forms of data is not enough, many vendors, such as IBM, have also included an obvious, though crucial, 5th V, value. This is the end game. After spending a lot of time, effort, and resources in setting up a big data initiative, one needs to make sure that actual value is being derived from doing so. This V refers specifically to the economic value of big data, as quantified using the total cost of ownership and return on investment. To illustrate the 5 V's of big data in more detail, let's have a closer look at some example sources or processes generating big data. A traditional source are large-scale enterprise systems, such as enterprise resource planning (ERP) packages, customer relationship management (CRM) applications, supply chain management, SCM systems, etc. Companies have been deploying these systems for about 2 decades now, yielding an unprecedented amount of data stored in various formats. The online social graph is another example. Think about the major social networks such as Facebook, Twitter, LinkedIn, Weibo, and WeChat. Altogether, these networks capture information about 2 billion people, their friends, preferences, and other behavior, leaving a massive digital trail of data. Also think about the Internet of Things, or the emerging sensor-enabled ecosystem that is going to connect various objects such as homes, cars, etc. with each other and with humans. Finally, we see more and more open or public data, such as data about weather, traffic, maps, macroeconomy, etc. Hadoop is an open source software framework used for distributed storage and processing of big datasets. The main difference between Hadoop and other attempts to work with huge volumes of data that came before is that Hadoop can be set up over a cluster of computers built from normal commodity hardware instead of requiring specialized, expensive machines. Hadoop is designed with the fundamental assumption that hardware failures are common occurrences and should be gracefully handled. Although Hadoop is managed by the Apache Foundation and is open source, many vendors offer their implementation of a Hadoop stack, which all differ in features, extra components, and support offered. In what follows, we first review the history of Hadoop and then elaborate on the Hadoop stack. The genesis of Hadoop came from the Google file system paper published in 2003. In this paper, researchers at Google introduced a new file system meant to support Google's growing storage needs. The goal was to develop a file system that could be easily distributed across inexpensive commodity hardware, whilst providing fault tolerance. This work led to another research paper from Google called MapReduce, Simplified Data Processing on Large Clusters. MapReduce introduced a programming paradigm to write programs that can be automatically parallelized and executed across a cluster of different computers. Around the same time, Doc Cutting was developing a new web crawler prototype, which would be better able to handle the growing web, called Nudge. The Nudge project had also implemented a MapReduce-based programming facility and a distributed file system. In 2006, Doc Cutting joined Yahoo. The part of Nudge which dealt with distributed computing and processing was split off and renamed to Hadoop, named after the yellow toy elephant of Cutting's son. In 2008, Yahoo open-sourced Hadoop as Apache Hadoop, since it was managed by the Apache Software Foundation. When talking about Hadoop in its pure form, with no additional components or technology, it is important to know that it describes a stack containing 4 modules. The first one is Hadoop Common, a set of shared programming libraries used by the other modules. The second is the Hadoop Distributed File System, HDFS, a Java-based file system to store data across multiple machines, renamed from NDFS in the Nudge project. The third module entails the MapReduce framework, a programming model to process large sets of data in parallel. Yarn, yet another resource negotiator, forms the fourth module and handles the management and scheduling of resource requests in a distributed environment. We elaborate on these components in what follows. Hadoop Distributed File System, or HDFS, is a distributed file system used by Hadoop to store data across a cluster of commodity machines. It lets users connect to nodes over which data files are distributed in a manner that allows for accessing and storing files as if it were one seamless file system, just as if you would work with a hard drive on your own computer. HDFS puts a high emphasis on fault tolerance, since it assumes that commodity hardware will commonly fail. Technology-wise, an HDFS cluster is composed of a name node and various data nodes. A name node is a server which holds all the metadata regarding the stored files. Think of this as a registry containing file names with their size and where to find their contents in the cluster. A name node manages incoming file system operations such as opening, closing, and renaming files and directories. It is also responsible for mapping data blocks, parts of files, to data nodes, which handle file read and write requests. Data nodes will create, delete, and replicate data blocks amongst their disk drives according to instructions from the governing name node. They continuously loop, asking the name node for instructions. Data replication is important to ensure fault tolerance. It is possible to specify how many replicas or copies of a file have to be created across different data nodes at the time it is created, a number which can also be changed after creation. The name node will make sure to then adhere to this request and distribute data blocks accordingly. The size of one data block is typically 64 megabytes. This figure illustrates the operations on HDFS. Note that a secondary name node server is provisioned if a failure of the name node occurs. The figure illustrates a basic metadata operation in action. The client consults the name node to find out which files are in the directory mydir. The name node maintains a registry of files and can immediately answer that one file is present with 2 replicas and that the size is 1 gigabyte. Next, our client wishes to read this file. It sends the name node a request to perform a read. The name node will look in its registry and instruct the client that it can read the first 64 megabyte data block from data node 1, the next block from data node 3, and so on. The client can then contact each data node to receive the contents of the file. In this figure, our client wants to create a new file and indicates this once again through a request to the name node together with the instruction to create 2 replicas. The name node responds with instructions regarding how to send the data blocks to the data nodes. The client will then contact the data nodes and start sending the contents of this new file. The work of the name node is not done yet, however. Every few seconds, data nodes will report in to the name node to indicate that they're still alive. In other words, send a heartbeat. And to update the name node regarding the blocks they are storing. The name node now sees that a recently written file has not yet been replicated and hence instructs the data nodes to perform the replication as illustrated in the figure. HDFS provides a native Java API to allow for writing Java programs that can interface with HDFS. Throughout the years, various ports and bindings have been created for other programming languages so they can communicate with HDFS. HDFS also comes with several command line commands to interface with HDFS. This code fragment shows a simple client program accessing HDFS from Java and reading out a file. Note, this example shows off an important remark when working with HDFS. Recall that the whole goal of HDFS is to split up potentially very large files and distributing them across machines. In this example, we're reading in a complete file and storing it in a byte array in memory of the computer executing the Java program. When working with big files, the received file size can easily exceed that of the client's available memory. Hence, it is important to construct programs in such a way that they can deal with files line by line or in limited blocks, such as shown here. You can see a listing of the most common Hadoop HDFS command line commands which allow you to access an HDFS cluster from the command line. MapReduce forms the second main important component of Hadoop. MapReduce is a programming paradigm made popular by Google and subsequently implemented by Apache Hadoop. MapReduce's main focus is on scalability and fault tolerance. A MapReduce pipeline starts from a series of values and maps each value to an output using a given mapper function. We utilize MapReduce when referring to the specific implementation in Hadoop. In many programming languages, this concept of applying a mapping exists natively, as this Python example illustrates. The reduce operation then applies a reducing function to a series of values, but now operates on the list as a whole instead of element by element. A list of values hence gets reduced to a single value as illustrated. A MapReduce pipeline in Hadoop starts from a list of key value pairs and maps each pair to one or more output elements. The output elements are also key value pairs. This operation can easily be run in parallel over the input pairs. Next, the output entries are grouped so all output entries belonging to the same key are assigned to the same worker. In most distributed setups, workers will correspond to different physical machines, so that also this step can happen in parallel. These workers then apply the reduce function to each group, producing a new list of key value pairs. The resulting final outputs are then optionally sorted by their key to produce the final outcome. Even though not all mapping operations have finished, reduce workers can already get started on their work by applying their reduce function on a partial group of results with the same key. When new mapped results come in, the reduce operation can be applied again to form the ultimately resulting outcome. This has two important implications. First, the reduce function should output the same key value structure as the one emitted by the map function, since this output can be used again in an additional reduce operation. Second, the reduce function itself should be built in such a way so it provides correct results, even if called multiple times. In Hadoop, MapReduce tasks are written using the Java programming language. To run a MapReduce task, a Java program is packaged as a jar archive and launched using the Hadoop command as illustrated here. Let's illustrate how a MapReduce task runs in a distributed cluster by constructing a Java program to count the appearances of a word in a file. To keep things simple, we'll write our program using one Java class as shown here. First, we need to define our mapper function. In Hadoop, MapReduce, this is defined as a class extending the built-in mapper key in, key out, value out class, indicating which type of key value input pair we expect and which type of key value output pair or mapper will emit. The mapper in our basic word counting example works like this. Our given input line will be split up in key value pairs as follows. Every line in the file will become one pair, with the key indicating the starting position of the line, which we don't need to use, and the value being the line of text itself. This will be mapped to multiple key value output pairs. For each word we emit a word 1 pair. The above table will be mapped to the below table. This operation will happen in parallel. Whilst our mappers are busy emitting output pairs, our reducers will start working. The reducer function is specified as a class extending the built-in reducer key in, key out, value out class. You can see this here. Our reducer works as follows. Keep in mind that the reducer works over a list of values and reduces them. Here, our list of values is a list of integer counts for a particular key, a word, which we sum and output as word, sum. To see how this works, imagine that our mappers have already emitted the above pairs. Since we already have duplicate keys for this and is, some reducers can already get started. Hence, the lower left table will be reduced to the lower right table. When later additional mapped output pairs appear with the key let me do that again. When later additional mapped output pairs appear with the key this, they can be reduced again to one output pair for this. Finally, we also need to add a main method to our Java program to set everything up, as you can see here. After compiling and packaging our program as a jar file, we can now instruct the Hadoop cluster to run our word counting program, as you can see above. Hadoop will start executing our MapReduce program and report on its progress, as you can also see illustrated. When finished, the user's me output directory will contain the contents shown here. What should be clear from this example is that constructing MapReduce programs requires a certain skill set in terms of programming. To tackle a problem, multiple ways of approaching it usually exist, all with different trade-offs in terms of speed, memory consumption, and scalability over a set of computers. There is a reason most guides and tutorials never go much further than a basic word counting or averaging example, and most organizations which have adopted the MapReduce framework in their data pipeline haven't been very eager to share their effort. Yet another resource negotiator, Yarn, distributes a MapReduce program across different nodes and takes care of coordination. Three important services are present in Yarn. First, the Resource Manager is a global Yarn service that receives and runs applications, an incoming MapReduce job for example, on the cluster. It contains a scheduler to govern the order in which jobs are handled. The Job History server keeps a log of all finished jobs, whereas the Node Manager is responsible to oversee resource consumption on a node. Node managers are responsible for setting up containers on a node, each of which can house a particular task, such as a single map or reduced task. By doing so, the node manager can also keep track of how busy a node is and whether it can accept more tasks at the moment. The whole Yarn setup can look daunting. Let us provide a step-by-step example as follows. This figure introduces a simple Yarn cluster with 4 servers, one of which is running the Resource Manager, one of which is running the Job History server, and 2 of which are running node managers. Or a client now wishes to submit an application to the cluster, like we submitted our word count program before. The client contacts the Resource Manager with a request to deploy and run a MapReduce program as shown here. The Resource Manager will keep our application in a queue until its scheduler determines that it is time to start our application. The Resource Manager will now negotiate with the Node Manager to instruct the setup of a container in which to start the application master. The application master will register itself on startup with the Resource Manager, which can then be kept up to date with further job status information. This also allows to relay this information to the client, which can then communicate directly with the application master for further job follow-up, as shown here. The application master will now handle the further execution of the submitted application, including setting up containers for map and reduce operations. To do so, the application master will ask the Resource Manager to negotiate with the node managers, who all report in regularly with the Resource Manager, to see which one is free. When a node manager is free, the application master will launch the container by providing necessary information to that node manager as shown here. When a map or reduce container is finished, it will deregister itself by letting the application master know it is done. This continues until the application has completed, at which point also the application master will send a completion update to the client and deregister itself with the Resource Manager and shuts down, allowing its container to be repurposed. The Resource Manager then contacts the Job History server to store a full execution log of this application in its archives. Yarn is a complex setup, but the architecture comes with many advantages. Yarn allows to run programs and applications other than MapReduce on its cluster as well. That is, Yarn can be used for coordination of any sort of task where decomposition into parallel subtasks is beneficial. This will become especially useful once we will move away from MapReduce, as we will see later. When working with Hadoop and MapReduce, it seems, however, that we are far away from the benefits that SQL offered us in terms of querying data, and even further from deriving business intelligence or analytical insights from it. The benefits of Hadoop, such as being capable to work with huge amounts of data, are understood, but the need for a more database-like setup on top of Hadoop becomes clear. In what follows, we discuss HBase, Pig, and Hive. The October 2007 release of Hadoop included the first version of HBase, the first Hadoop database inspired by Google's Bigtable, offering a DBMS that can be run on top of HDFS, handling very large relational tables. It hence puts some logical structure on top of HDFS. Note that HBase, with its focus on large datasets and emphasis on running in a distributed fashion, can be regarded as one of the older NoSQL databases. HBase is hence also more a data storage platform rather than a true DBMS, as it still lacks many features you find in a relational DBMS, such as typed columns, triggers, advanced query capabilities, and so on. Instead, HBase focuses on offering a simplified structure and query language in a way that is highly scalable and can tackle large amounts of volume. Just as a relational DBMS, HBase also organizes its data in tables, which have rows and columns. Still, the similarities end here, as it is more helpful to think of HBase's tables as being multidimensional maps or multidimensional arrays as follows. An HBase table consists of multiple rows. A row consists of a row key and one or more columns with values associated with them. Rows in a table are sorted alphabetically by the row key, making the design of this key a crucial factor. The goal is to store data in such a way that related rows are near each other. Each column in HBase is denoted by a column family and an optional qualifier separated by a column, such as name first and name last. A column family physically co-locates a set of columns and their values. Each family has a set of storage properties, including whether its values should be cached, whether values should be compressed, and so on. Every row in a table has the same column families, but not all column families need to have a value filled in for each row. The column qualifier is added to the column family to provide an index of a certain piece of data. Each cell in a table is hence defined by a combination of the row key, column family, and column qualifier and a timestamp. The timestamp represents a values version and is written alongside each value. To show how this works in practice, let's create a simple HBase table to store and query users using the HBase shell. The row key will be the user ID. We'll construct the column family's qualifiers as illustrated here. Let's start by creating our users table with two column families. We then describe the table using the describe command. Note that the statement will return a lot of additional configuration information as illustrated. Here you can see another way to list this table. We can now start inserting values. Since HBase represents data as a multidimensional map, we store values using put one by specifying the table name, a row key, column family, and qualifier, and the value itself. The scan command is used to list the full contents of this table. We can then use get to select a single row key. For example, give the information for row key SEPA only. We can change the email value by just running put again as illustrated. Note that HBase's query facilities are very limited. Essentially, HBase offers a column-oriented key-value distributed data store with simple get and put operations. Like MongoDB, HBase includes facilities to write MapReduce programs to perform more complex queries, but once again, this comes at an extra cognitive overhead. When using HBase, make sure that you really have that much data to warrant its usage in the first place. For example, if you have hundreds of millions or billions of rows, then HBase is a good candidate. If you have only a few million rows, then using a traditional RDBMS might be a better choice, because all your data might wind up on a few nodes in HBase anyway, and the rest of the cluster may be sitting idle. Finally, make sure you have enough hardware available. HBase, just as the rest of Hadoop, doesn't perform that well on anything less than 5 HDFS data nodes with an additional name node. This is mainly due to the way how HDFS block replication works, which only makes the effort worthwhile when you can invest in, set up, and maintain at least 6 to 10 nodes. Yahoo developed Pig, which was also made open source as Apache Pig in 2007. Pig is a high-level platform for creating programs that run on Hadoop in a language called Pig Latin, which uses MapReduce underneath to execute the program. It aims to enable users to more easily construct programs that work on top of HDFS and MapReduce and can somewhat resemble querying facilities offered by SQL. This Pig Latin fragment shows how a CSV file, comma-separated values file, from HDFS can be loaded, filtered, and aggregated. The $1 and the $0 and $1 symbols refer to column numbers in the CSV file. Some have argued that RDBMSs and SQL are substantially faster than MapReduce, and hence Pig, especially for reasonably sized and structured datasets and when working with modern RDBMS engines. In addition, Pig Latin is relatively procedural versus SQL's declarative way of working. Pig has not seen wide adoption and does not receive frequent updates. Only one version was released in 2016. The question hence remains whether supporting SQL as is on Hadoop is possible. Hive was initially developed by Facebook, but was open sourced later. Hive is a data warehouse solution which, like HBase, runs on top of Hadoop but allows for richer data summarization and querying facilities by providing an SQL-like interface. Hive provides the necessary abstraction layer to convert SQL-like queries to a MapReduce pipeline. Hive also offers a JDBC and ODBC interface. Hive can run on top of HDFS as well as other file systems such as Amazon's S3 cloud storage file system. Architecturally, Hive puts several additional components on top of Hadoop. The Hive metastore stores metadata for each table, such as their scheme and location on HDFS. It is remarkable to note this metadata is stored using a traditional RDBMS. The metastore helps the rest of the Hive system to keep track of the data and is a crucial component. The driver service is responsible to receive and handle incoming queries. It starts the execution of a query and monitors the lifecycle and progress of the execution. It stores the necessary metadata generated during the execution of a query and acts as a collection point to obtain the query result. To run a query, the compiler will first convert it to an execution plan containing the tasks needed to be performed by Hadoop's MapReduce. This is a complex step where the query is first converted to an abstract syntax tree, which, after checking for errors, is converted again to a directed acyclic graph representing an execution plan. The directed acyclic graph will contain a number of MapReduce stages and tasks based on the input query and data. The optimizer also kicks into gear to optimize the directed acyclic graph, for instance, by joining various transformations in a single operation. It can also split up tasks if it determines this will help performance and scalability once the directed acyclic graph runs as a series of mapping and reduce operations. Once the directed acyclic graph is compiled, optimized, and divided into MapReduce stages, the executor will start sending these to Hadoop's resource manager, Yarn usually, and monitor their progress. It takes care of pipelining the stages by making sure that a stage gets executed only if all other prerequisites are done. Though Hive queries strongly resemble SQL, HiveQL, as Hive's query language is named, does not completely follow the full SQL 92 standard. HiveQL offers several helpful extensions not in the SQL standard, such as allowing for inserts in multiple tables at once, but lacks strong support for indexes, transactions, materialized views, and only has limited subquery support, so some very complex SQL queries might still fail when trying to execute them on Hive. Here you can see an example of a HiveQL query. Note that this automatically gets converted to a MapReduce pipeline behind the scenes. In addition, the fact that Hive stores its data tables on top of HDFS also makes the query language particularly well suited when datasets other than structured tables need to be queried, as long as it is possible to express a statement to extract data out of them in a tabular format. This query illustrates the word count example using HiveQL. One difference with traditional DBMSs, however, is that Hive does not enforce the scheme at the time of loading the data. A traditional RDBMS, for instance, can store data with a scheme already being defined, meaning you have to define your scheme ahead of time. This is also called scheme on write. The scheme is applied and checked when data is written to the data store. Hive, on the other hand, applies a scheme on read approach, where tables can just be defined over a series of input files, but where the scheme check will occur as the data is being queried and read from the data store. In this way, you can quickly load your data into the data store and figure out how to parse and handle it later. Recent versions of Hive support full asset transaction management. Performance and speed of SQL queries still forms the main disadvantage of Hive today. Since there is still a large overhead in setting up and coordinating a series of MapReduce tasks, even relatively simple Hive queries can already take a few hours to complete. Solutions have been suggested to bypass MapReduce, such as Apache Test, Cloudera Impala, and Facebook Presto. Researchers at the University of California started working on an open source alternative for MapReduce in 2014, Spark, a new programming paradigm centered on a data structure called the Resilient Distributed Dataset, or RDD, which can be distributed across a cluster of machines and is maintained in a fault-tolerant way. Spark was developed with a specific focus on offering a response to the limitations that MapReduce had. Whereas Spark still enforces a relatively linear and fixed data flow structure, in other words, mapping and reducing data, Spark's RDDs allow you to construct distributed programs in a way where a cluster's memory can be used as a shared distributed resource, opening the possibility to construct a wide variety of programs. That is, RDDs can enable the construction of iterative programs that have to visit a dataset multiple times, as well as more interactive or exploratory programs, which is exactly the type of programs one would need to facilitate the querying of data. The Spark team showed this approach was many orders of magnitude faster than MapReduce implementations, and Spark has hence been extremely rapidly adopted by many big data vendors in recent years as the way forward to exploring, querying, and analyzing large datasets. Note that Spark is not completely different from Hadoop in terms of setup. It still works with a HDFS as a distributed storage system or other storage systems such as Amazon's S3, and still requires a cluster manager such as Yarn as well. The MapReduce component, however, is what Spark aims to replace, as well as offering additional components on top of the Spark core to facilitate a number of data analysis practices. In what follows, we discuss these components in more detail. The Spark core forms the heart of Spark and is the foundation for all other components. It provides functionality for task scheduling and a set of basic data transformations that can be used through many programming languages such as Java, Python, Scala, and R. To do so, Spark introduces a programming model based around the concept of resilient distributed datasets, RDDs, the primary data abstraction in Spark. RDDs are specifically designed to support in-memory data storage and operations, distributed across a cluster so it is both fault-tolerant and efficient. The first is achieved by tracking the lineage of operations applied to coarse-grained sets of data, whereas efficiency is achieved through parallelization of tasks across multiple nodes, whilst minimizing the number of times data gets replicated or moved around between them. Once data is loaded into an RDD, two basic types of operations can be performed. Transformation, which creates a new RDD through changing the original one, and actions, such as counts, which measure but do not change the original data. The chain of transformations gets logged and can be repeated if a failure occurs. One might wonder what makes this approach so much faster than the MapReduce pipeline. The reasons are as follows. First, transformations are lazily evaluated, meaning they are not executed until a subsequent action has a need for the result. When possible, RDDs will also be kept as long as possible in memory, greatly increasing the performance of the cluster. This is a big difference with MapReduce, as this approach writes and reads data a lot throughout its pipeline of map and reduce operations. Finally, a chain of RDD operations gets compiled by Spark into a directed acyclic graph, similar as Hive did for HiveQL queries, but which is then spread out and calculated over the cluster by splitting up this computational graph into a set of tasks instead of converting it to a set of map and reduce operations. This greatly helps to speed up operations. This figure shows Spark's general approach. A big advantage for end users is that Spark's RDD API is relatively pleasant to work with compared to writing MapReduce programs. Even map and reduce operations can still be expressed through the concept of RDDs, which can hold a collection of any type of object, as this Python code sample shows. Spark's RDD API can be daunting when coming from an SQL background or being used to working with data that is structured, such as tabular data. To allow for a user-friendly way of working with such structured datasets, Spark SQL was devised as another Spark component which runs on top of Spark Core and introduces another data abstraction called data frames. Data frames can be created from RDDs by specifying a scheme on how to structure the data elements in the RDD, or can be loaded directly from various sorts of file formats such as CSV files, JSON files, from a JDBC query result, and even from Hive. Even although data frames continue to use RDDs behind the scenes, they represent themselves to the end user as a collection of data organized into named columns. This is done to make processing of large but structured datasets easier. This Python code fragment shows Spark's data frames in action. Here you can see the example continued. And here as well. Even although the previous statements resemble SQL, they are not completely alike. However, remember that underlying the data frame API, which you can use in Python, Java, and other languages, the concept of RDDs is still being used to execute your operations. To do so, Spark implements a full SQL query engine which can convert SQL statements to a series of RDD transformations and actions. This is similar to how Hive converted SQL statements to a MapReduce pipeline. The difference is that Spark's Catalyst query engine is a powerful engine which can convert SQL queries in a very efficient RDD graph. All code examples we have just seen are converted to an SQL statement, which is then transformed to an RDD program. It is just as well possible to directly write SQL in your programs to manipulate data frames if you prefer, hence the name Spark SQL. You can see an example of this here. The last Spark components we need to mention are MLlib, Spark Streaming, and Graphx. MLlib is Spark's machine learning library. Its goal is to make practical machine learning scalable and user-friendly. MLlib offers classification, regression, clustering, and recommender system algorithms that originally worked on top of the RDD paradigm. The new MLlib version works directly with Spark SQL's data frames-based API, as many machine learning algorithms assume data to be formatted in a structured, tabular format anyway. Also, Spark Streaming leverages Spark Core and its fast scheduling engine to perform streaming analytics. Spark Streaming provides another high-level concept called the D-stream, discretized stream, which represents a continuous stream of data. Internally, however, a D-stream is represented as a sequence of RDD fragments, with each RDD in a D-stream containing data from a certain interval. Similar to RDDs, most of the same transformations can be applied directly on the D-stream, allowing its data to be modified. D-streams also provide windowed computations, which allow to apply transformations over a sliding window of data. Different D-streams can also easily be joined. This Python example shows a word counting program which now works over a continuous stream of data. Graphx is Spark's component implementing programming abstractions to deal with graph-based structures, again based on the RDD abstraction. To support common graph computations, Graphx comes with a set of fundamental operators and algorithms such as PageRank to work with graphs and simplify graph analytics tasks. Also here, work has been put underway for Spark to provide the same graph-based abstractions on top of data frames, called graph frames, although this is still very much a work in progress. This chapter has discussed big data and the most common technology stack supporting it. We have started our discussion from the 5 V's of big data, namely volume, velocity, variety, veracity, and value. From there, we have reviewed various big data technologies, starting from Hadoop. We saw, however, how Hadoop's raw stack is unable to support strong querying capabilities, leading to various solutions to bring the DBMS to Hadoop, so to speak. HBase and Pig were amongst the first vendors in this space, with HBase being an example of a NoSQL database on top of Hadoop, still offering, however, limited query capabilities, and Pig trying to offer a friendlier programming language on top of MapReduce. Hive was introduced as the main project, bringing the power of SQL to Hadoop, but still being limited by the MapReduce paradigm. Finally, Spark was introduced, doing away with MapReduce altogether and replacing it with a directed acyclic graph-based paradigm with a strong SQL engine offering performant query capabilities and machine learning, streaming, and graph-based components. If you want more information about this, we are happy to refer to our book Principles of Database Management, published by Cambridge University Press. See also the website at the bottom of my slide.